Hello viewers, in today's session we are going to discuss some important problems related to linear differential equations of this form, that is dx over dy plus px is equal to q, right? So here we'll solve some problems related to this form of linear differential equation, and this linear differential equation is of first order and first degree, right? And here p and q are some functions of y or constant. So p is a function of y and q is also a function of y, or p may be a constant, and similarly q may be a constant. So now in order to solve linear differential equations of this type, we need to find out the integrating factor, right? And the integrating factor of this type of linear differential equation is given by e raised to integral p dy. And once we find out the integrating factor of this linear differential equation, we can write the solution of this linear differential equation as x times the integrating factor, and then we have the integral and q times integrating factor, and here we have dy, and c is the constant of integration, right? So this equation gives us the general solution of linear differential equation of this form: dx over dy plus px is equal to q. And here y is the independent variable and x is a dependent variable. So let us solve some examples. So let us solve this differential equation. So here we have y dx minus in bracket we have x plus 3y cube dy is equal to 0. And here we are given an initial condition, that is y of 1 is equal to minus 1. So the first step is to reduce this linear differential equation in this form. So what we will do, we'll write here y dx, and then we'll take this term to this side. So we have x plus 3y cube, and here we have dy. So now we can write this expression as dx over dy, and we can take this y in the denominator of x plus 3y cube. So we have x plus 3y cube over y, and now we can write it like this: x over y, and then we have 3y cube over y, and this is x over y plus 3 y square. So here y get cancelled, right? Okay, so now we can transfer this term to the left hand side. So we have dx over dy minus x over y, and here we have 3y square. So we can also write this equation as dx over dy, and then we have plus, and here we can write minus 1 over y, x, and 3y square. So now this equation is of this form. So here we have dx over dy, and then we have px. For p, we have minus 1 over y, and for q, we have 3y square. And from p and q, we can easily see that p and q are functions of y. So now let us find out the integrating factor of this differential equation. So the integrating factor is given by e raised to integral p dy. P is minus 1 over y, and here we have dy, and we can now write minus, and we have 1 over y dy. So the integral 1 over y dy is simply a log of y. and here we can now write e raised to natural log of y raised to minus 1. So we can now write here simply y raised to minus 1, that is 1 over y. So here we have used this result, that is e raised to natural log of say x is equal to x, right? And here we have used the property of logarithm, so taking minus sign in the power of y, right? And here we have e raised to natural log of y raised to minus 1, and due to this result we have simply y raised to minus 1, that is 1 over y. So now let us write the solution of this differential equation using this expression. So we have x times integrating factor, which is 1 over y, and then we have the integral q is 3y square, and integrating factor is 1 over y and dy, and c is the constant of integration. So we have x over y, and here y and y get cancelled. So we have integral 3y dy plus c, and we have 3 times the integral y dy plus c, and here the integral y dy is simply y square over 2, and c is the constant of integration. So we have now this expression x over y is equal to 3y square over 2 plus c. Now we can multiply this term by y, and we have now x is equal to 3y cube over 2, and here we have cy. So this is the general solution of this differential equation involving one arbitrary constant, right? And here we can see that the right hand side is in terms of y only. So the solution is of this form, that is x is equal to f of y, right? Where y is the independent variable and x is the dependent variable. So now to get the value of this arbitrary constant c, we have to make use of this condition. So here for x is equal to 1, we have y is equal to minus 1. So substituting these values in this equation, we have 1, then we have 3 over 2 and minus 1 cube, and here we have c times minus 1. So we have 1 minus 1 cube is minus 1, so we have minus 3 over 2, and here we have minus c. So from here we can now write minus c is equal to 1 plus 3 over 2, that is 2 plus 3 over 2, that is 5 over 2, and c is minus 5 over 2. So the value of this arbitrary constant c is minus 5 by 2. So substituting this value of c in this equation, we can get the particular solution of this differential equation as x is equal to 3 over 2 y cube, and here we have minus 5 over 2, and here we have y. So this is the particular solution of this differential equation, and this represents the general solution of this differential equation. So now consider this problem. Here we have y e raised to y dx is equal to y cube plus 2x e raised to y and dy, and y of 0 is equal to 2, right? So let us first try to transform this equation into this form. So what we will do, we'll write here dx over dy, taking dy over this dx, and here we have y cube plus 2x e raised to y, and divided by this term, that is y e raised to y, right? And now from here we can write this equation as y cube over y e raised to y, and then we can write 2x e raised to y over y e raised to y. So now we can write dx over dy is equal to, here this y get cancelled, and we have y square over e raised to y, and then we have here e raised to y and e raised to y get cancelled. We have 2x over y. So now we can write dx over dy minus 2x over y, and here we have y square over e raised to y, so we can write it as e raised to minus y. So taking this term to the left hand side. So now we have dx over dy, and then we can now write minus 2 over y, and here we have x, and here we have y square e raised to minus y. So now this equation is of this form, where the value of p is given by minus 2 over y, and q is given by y square times e raised to minus y, and p and q are both functions of y. So let us first find out the integrating factor. So integrating factor is given by e raised to integral p dy. So we have e raised to integral p is minus 2 over y. Here we have dy. So now we have e raised to minus 2, taking minus 2 outside this integral sign, and we have 1 over y dy. So this is e raised to minus 2, and the integral of 1 over y dy is the natural log of y, right? So now using the properties of logarithms, we can take minus 2 to the power of y here. So we have e raised to natural log of y raised to minus 2, and this is simply y raised to minus 2, that is 1 over y square. So here again we have used this result. E raised to natural log of say x is equal to x. So here we have for x we have e raised that is y raised to minus 2, and we have the integrating factor as 1 over y square. So now the general solution of this differential equation can be written with the help of this equation. So we have x times integrating factor, that is 1 over y square, then integral, and the value of q is given by y square and e raised to minus y, and the integrating factor is 1 over y square, and here we have dy, and c is the constant of integration. So we have x over y square, and here this y square and this y square get cancelled, and we have e raised to minus y dy and c, right? And we can now write x over y square is equal to the integral e raised to minus y dy plus c. So the integral e raised to minus y dy is minus e raised to minus y, and here we have c. So now multiplying this quantity by y square, so we have x is equal to minus y square e raised to minus y, and plus c times y square. So this is the general solution of this differential equation containing this arbitrary constant c. So now let us find out the value of c using this condition. So we have y is equal to 2 when x is equal to 0. So substituting these values in this expression, we have 0, and here we have minus 2 square e raised to minus 2, and here we have c times y square is 2 square, right? So we have 0, here we have minus 4 times e raised to minus 2, and this is 4 times c. Now dividing both sides by 4, we can get rid of this 4. So we have now 0 is equal to minus e raised to minus 2 plus c, and taking this term to this side, we have c is equal to e raised to minus 2. So the constant of integration c has the value e raised to minus 2. Now substituting this value in this expression, we have now x is equal to minus y square e raised to minus y plus e raised to minus 2, and here we have y square. So this is the particular solution of this differential equation.